Hello, my name is Professor Matthew Schmidt, and welcome to Genetics. In this section, we're going to talk about the application of sex-linked traits to human genetic analysis. We did this once before when we talked about the application of regular Mendelian traits, and we found out that since you can experiment freely with things like peas and fruit flies, but not with humans, that we often have to rely on a pedigree analysis, which is basically a family history, in order to try and figure out the way in which a particular allele is passed on. Now, when we did it the other time, we talked about just the difference between a dominant and a recessive. And if you remember the term, we talked about only autosomal dominance and recessive. Autosomal means non-sex linked, and remember we talked about the chromosomes being autosomes that are not the sex chromosomes. What we want to do now is sort of integrate the idea of sex linkage by finding out, okay, once we know something's recessive or dominant, can we further tell whether it's sex linked? That is, in most cases that means the gene is located on the X chromosome, or is it autosomal, in which it's not located on the X, it's located somewhere else. In the problem-solving section, you'll find some more challenging examples of these types of problems, and since this is sort of a theory session, we're going to look at problems, but we're going to try to understand ways of what's going on here, how can we use the information, etc. So I call this part pedigrees, tips, and tricks. They're not really tricks, but what I mean is there are certain little shortcuts, which also sounds bad, but if they're applied correctly, you can save yourself a lot of time in trying to figure out one of these pedigree analyses. They can look quite daunting. Some of them actually are daunting. But a lot of times, if you can look at it in the right way, you still have to do your detective work, but you may be able to save yourself quite a bit of time and mental anguish, I dare say. So let's get a couple of things down here. Generally speaking, if a trait is sex-linked, and remember, we're talking about X-linked traits, those in which the gene of interest is on the X chromosome. It's not written in stone, but in real life, this is generally true, that more males are affected than females are. The reason is because since males only have one X chromosome, they have no other possible allele to sort of shield the expression, especially if it's a recessive trait. It's not necessarily the case. In other words, pedigrees can be designed, if someone wants to trick you, where it is in fact sex-linked, but more males are not in fact affected than females. But if you see that, it's a good sort of starting point. And don't get me wrong, females certainly can be affected, so you can't rule that out. That's just sort of a tip. If you see all males affected and no females, you might want to think about sex linkage. We said this next one before, but we want to remember it again. If a trait is referred to as rare or extremely rare, what that's trying to get into your mind is that people coming into the pedigree from outside the family, marrying into the family, do not carry the allele of interest, whether it's dominant, recessive, sex-linked, or whatever, unless the data prove otherwise. So if you see in the data that you see someone coming in from outside the family and there's evidence that they do carry either a trait or an allele, then that's the way it is. Data is data. But if it's rare and you don't see that, you're allowed to make that assumption. And again, while it's not proof, crisscross inheritance, if you see it consistently happening, it is a characteristic of sex linkage. Okay, so what I'd like to do is take a look at an actual couple of pedigrees, and here's one where it tells you right off the bat this is an X-linked or sex-linked recessive, and it's hemophilia. There are a variety of types of hemophilia, but the most common one is a sex-linked recessive trait. So in this pedigree, remember the conventions we discussed: circles equal females, squares equal males. Shaded in individuals have the disease, in this case hemophilia. they're showing us one other thing in this pedigree that you may or may not be shown if you're given a problem, and that is they're telling us who's a carrier and who's not a carrier. Now, since we know that this is X-linked from the beginning, a male could never be a carrier, right? Because if you have the allele, you're showing the disease. If you don't, you're not. So that's one thing about sex linkage. For a recessive trait, a male could not be a carrier, but females can, and they're being shown, as you see in the legend up here, as they have a circle with a little circle inside that's purple. Usually you probably wouldn't be shown that information, but remember, in this type of a session, we're trying to understand what's going on in these pedigrees. You can apply them later in the problem-solving sessions. So basically, one thing you can do is, I told you this before, there's no absolute 100% rule about how to approach these pedigrees. You have to do some trial and error. You have to look around and sort of see what you see. So one thing that I would notice just right off the bat is that let's look at all the affected individuals. And by the way, I should have mentioned this is an actual pedigree of part of the royal family of Queen Victoria. There was hemophilia in that family, and these are actual, it's not the complete pedigree of everyone, but it's sort of pieces of interest. So this is real data. Notice that all of the people who actually have hemophilia, Leopold, Rupert, Alexis, and some other dude that we don't know his name, they're all males, right? So while it's not proof, this does go to the idea right off the bat. If you didn't know already, you might say, this has the characteristics. I don't see any females being affected. Only people who are affected are males. That sounds sex-linked to me. So you keep that in mind. We also want to say, if we were approaching this from the point of view of just what is this, is it dominant or recessive? Well, you can tell it's recessive right off the bat by the same principle we used before, right? Rupert's not the only one, but he's got the disease, and neither of his parents have the disease. We said that that's the hallmark of a recessive trait. So this is more about the sex-linked aspect, but I just want you to realize that it's definitely recessive. So then the question becomes, is it X-linked or is it autosomal? I know you know it's X-linked, but let's see how we can sort of prove that. Well, one way is, let's take a look, do what we did before and see if we can tell the genotypes of these individuals. Given that it's sex-linked, let's try that first, and then we'll try it if it was autosomal and see if that works or doesn't work. One thing is for sure. So the way we did it last time is we said, here's the hypothesis. Let's just make it easy. The hypothesis is that the hemophilia allele is sex or X-linked. So in that case, anyone who has it, right, Leopold, for example, has to be, arbitrarily, I'll just use H for hemophilia. He's got to be X little hy. We already established it's recessive, right? Now, what this means is, if Leopold had a daughter, remember, males always give their X chromosome to their daughter, and he did have one daughter, so here she is. We know she has to have at least that. Now, since she's a carrier, she also has to have one big H. It's lucky we could see she's a carrier here. Where did that big H come from? It came from her mom, Helene, who was coming from outside the family. So the implication is that she was homozygous, right? But regardless, we know that she gave one X with a big H to her daughter. That's what makes her a carrier, all right? So that's sort of consonant with the idea of sex linkage. Since there are no affected women, it's hard to really, ask ourselves, well, here's an affected woman. Let's see how the behavior is with her. But you can do one thing. If we start putting in genotypes here, Queen Victoria was a carrier, right? And we can sort of follow this down. Prince Albert, assumedly, was not. So here's all the kids they had in generation 2. Victoria, Alice, Edward, Alfred, Louise, Arthur, Beatrice. Helena is supposed to be a male, as it says here. I don't know about that, but we're going to have to take for granted that she's a male. So think about this. All these kids, notice none of them are affected. Why are they not affected? Every one of them got this, X with a big H from Prince Albert, their father, right? Every single one of them. That means if you're a male, that's the only allele you have, and you're not going to be affected. But also what it means is Queen Victoria could have given X with the big H or X with the little h. And you can see that on this chart where Victoria here is not a carrier. So we know she got one big H from her dad. She also got a big H in this case from Queen Victoria. Alice is a carrier, so that means she got the little h from her mother, Queen Victoria. And you can go all along here and see how that happened. You can also see how the people who are affected, this is an interesting thing that you might want to keep in mind. We mentioned that males always give their X chromosome, right, to their daughters. By the same token, men always get their X chromosome from their mothers, right? So a person like this who is affected, and we know that that genotype has to be like this, he had to get Y from his dad, right? That doesn't matter if he's affected or not, even though he's not. So he had to get the X little h from his mom, Alice, who we know was in fact a carrier. So all of this makes sense in terms of sex linkage. Let's take a look at, I'm going to do a lot of erasing, so if you want to pause this to look it over, feel free to do so. Another thing just to mention, you do see skipping of generations here. The reason I bring it up is if a trait was dominant, whether it be sex-linked or not, remember that any offspring with the trait has to have a parent that also has the trait, so you don't see that skipping of generations. Okay, I'm going to erase a good amount of this. What if we had a hypothesis that this was recessive, but that it was autosomal recessive? Well, we might have to invoke the rare rule, if you remember the rare rule that we just mentioned, but I didn't do a great job at erasing, did I? All right, so we're now going to assume in our hypothesis 2 that it's autosomal. Now, if it's autosomal, even though there are only men affected here, it shouldn't matter. Let's use the letter H, and we'll just say they all have to be little h, right? So here's the thing with that. That obviously means that they had to get a little h allele from both parents, correct? Let's look at Rupert again here. The fact that the mother's a carrier, see, that's well, we could say she was a carrier in the sense that she's a heterozygote, but for now let's just, well, we could say that. All right, so that means he got one little h from his mother. He had to get one little h from his father, and what it comes down to is, could the father be a carrier? It's humanly possible, but if you're told that this is rare, you have to assume that people coming from outside the family are not carriers, right? Are homozygous, unless there's any evidence to the contrary. And there is no evidence to the contrary here. So if this guy, whoever he is, was big H, he'd have to give the big H allele to all of his offspring. And if this was in fact autosomal recessive, under those conditions, none of them would be able to be affected. So sometimes, often in fact, the only absolute way to prove, which is a strong word, but to really be convinced that something is sex-linked recessive, is to invoke the rare rule, and also to use all these other things we've been talking about with respect to males being more affected. And remembering that an affected male had to get, if it's sex-linked, he had to get that X chromosome from his mom, and that he's going to be giving it to his daughters as well. All right? So basically, it's an extension of what we've already done, and if you're presented with a problem like this, you may have a lot or a little less information than this. Really keep an eye out for that rare idea, because sometimes it's the only way to be sure. And like I said, you can look at this and you can say, well, only men are affected, that means it's sex-linked. Most of the time you'll be right, but some sneaky professors, and I know because I've been one of them sometimes, will purposely figure out a way to make a pedigree so that it looks like, well, males are affected, but in fact it's not necessarily sex-linked. Most of the time it is, but Just be careful, okay? Well, let's look at an X-linked dominant 1 now. Now this is, again, we're telling you right off the bat that it is in fact X-linked dominant. In a regular problem, you'd probably be starting from scratch. This is a disease called hypophosphatemia. You don't really need to worry about it. Hypophosphatemia, there are a lot of reasons this can happen. It's a cause of rickets. Now you may have thought that rickets is because of vitamin D deficiency, and it usually is. But since bone is made of calcium and phosphate, if you have a problem with phosphate, vitamin D or not, you're going to have a big problem making bones, which mimics the symptoms of regular rickets. So anyway, there are other reasons to get it, but there is one form of it that is a genetic condition that's X-linked dominant, okay? Now, one thing you could see here just in terms of, think of the dominant part, we're seeing that every single individual that's affected, and in this case, check this out, number 1. In this case, there are not more males affected than females. You could count them all up, and I encourage you to do it, but it turns out there are more affected females here than there are males. So that's not the only way to do this, right? One thing is for sure, though, whoever is affected does have a parent who's affected, and that goes along with the idea of dominance, right? In fact, now one thing about this pedigree I should have mentioned, I'm sorry, it's not showing you all the parents, unfortunately, but the reason is because they're saying this is so rare that anyone coming from outside the family is in essence irrelevant because they're not bringing one of the alleles in. So what you're seeing here is some parents up here, assumedly, made these children. They're all affected with the disease, and then we're seeing, yeah, they all had to, marry or procreate with someone in order to have their offspring, but they're not showing that other person because we're assuming that they're unaffected. That's allowed. You're allowed to do whatever you want as long as you say it. So what can we see here in terms of? Well, one thing is we never see an affected person with two unaffected parents. You can look all over, but you're never going to see that, even though you're assuming that one of the parents is always unaffected. That means in this type of analysis, the parent that you do see always is going to be affected, and that's what you see here, right? So that suggests dominance, absolutely. As far as recessiveness goes, if you wanted to real quick make a hypothesis that it's recessive and very rare, we could say this. So here's a person, if it was recessive, they're little a, right? The person they married was not another man. Not that there's anything wrong with that, but they would have trouble procreating. So I'll draw a circle there. If they're coming from outside the family, they'd have to be big A, right? And if this was recessive, that means that none of their offspring could be affected, and yet they are. So that gets rid of the whole idea of recessiveness. So now we were back to being dominant, and we're trying to figure out if it's X-linked or sex-linked dominant or not. Unfortunately, you guys, this is one situation where it's almost impossible to prove one versus the other. But you can get to a high, very high probability where you can say that this is X-linked X-linked dominant as opposed to autosomal dominant. Let's see how you can do that. The key often is looking at the males and asking questions about them. So if we have a hypothesis that it is X-linked dominant, right? We've gotten rid of the recessive idea here. Let's go through some of the genotypes. So let's look at this person right here. And why don't we make the gene H again for hypophosphatemia? So if it's X-linked and dominant, this guy would have to have X big H Y, right? Now remember this, males always get their X chromosome from their mother. So if this is sex-linked, what that would mean is anytime you see an affected male, his mother has to be affected too. Because with dominance, there's no carrier. If you have the allele, you're showing the disease, right? So if every single male has an affected mother, which seems to be the case, I'm looking for males with an affected mother. Every single affected male here that we see has an affected mother, correct? And remember this as well. Mothers give their X chromosome to their son, but mothers have two X chromosomes, so it's a little harder to say. An affected mother could give that one X with the dominant disease allele to her son, but she might not give it to her son. She could give it to her daughter, or she might not. So the bottom line is that all of this information is reasonably consonant with the fact of it being the other hypothesis, that it's autosomal. In fact, if you looked and did the most detailed analysis in the world, you really couldn't prove whether it's autosomal or whether it's X-linked. So here's the best you can do, is to say, so one other thing is this, sort of the reciprocal, the opposite of what I just did, I'll do in red, is we looked at affected males and said, listen, if it's X-linked, their mothers have to be affected too, and we saw that that was the case. What about looking at affected males and their offspring? Here's another affected male. They also have to have the genotype if this is true. Now, is it not true that males give their X chromosome to their daughters? It is. And if it was a dominant disease, it means that all of the daughters of an affected male would also have to be affected. Let's see if that's true. Let's look at all the affected males and see if their daughters are affected. Yes, 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 yes. You don't see any. Yep. Now in the next generation, this guy's daughter, his sons are not affected. Notice that. And that's all the information we have. So this is a strong, strong indication, guys, because if it was autosomal, there'd be no pattern whatsoever with respect to this fathers giving it to daughters, daughters giving it to sons. It's like that crisscross inheritance that we discussed. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, over 10 instances where in theory it could have been either sex, and consistently every single time we're seeing a situation that would happen if it was X-linked. It's not proof, but it's good enough in the lack of any other evidence to basically say the strong, strong likelihood is that this is going to be X-linked. We know it's dominant. Okay? So be careful of what they're asking. Sometimes you could prove beyond the shadow of a doubt. In this type of a case, it's more that the preponderance of the evidence, as they say in court, shows you that this is the case. All right? Now, I wanted to introduce two other terms that you may or may not have to learn, but if you hear them, it's very important you don't confuse them with what we've just been talking about. Sex-limited and sex-influenced traits have absolutely nothing to do with sex linkage. Sex linkage, after all, remember, we said the traits are on the X chromosome, but they don't really have anything to do with sex per se. Well, these type of traits have to do with sex in a certain sense. So let's see what it means. Sex-limited traits, they're not even usually on the X chromosome. They could be, because remember, the X chromosomes can have genes on it about anything. But here is the bottom line of sex-limited. These are traits that only manifest, they only come out in one sex. Now the example I'm going to give you may seem very odd, but it's a perfect example really, and it's formation of ovaries in humans. I don't know if you ever thought about this before, but human babies, or I should say embryos, are gender neutral for a couple of weeks of their very early life. They have the possibility of going down the male route or going down the female route. Males and females pretty much have the same genes. It's just a matter of which ones are getting activated. So if I asked you, I think it's going to sound odd, do I or you, if you're a man, have the genes in me that know how to make ovaries? Of course we do. Why didn't I make ovaries? Because the hormonal environment was not conducive to that. It mainly has to do with the amount of testosterone present, but there are other factors too. So both sexes, I mean, look, I know sometimes men and women can seem like they're totally on different wavelengths, but, you know, that's probably more of a, I don't know anything about it. But my point is, we have the same genes. It's just a matter of which are manifest and which aren't. So since women only have ovaries, that's the perfect example of a sex-limited trait. It's limited to females. Men could, in theory, express that trait, but they don't do it because of the fact that they're males in the hormonal environment. Now, sex-influenced traits are perhaps more interesting in that males and females could exhibit them, but they tend to act very interesting, as dominant in one sex and as recessive in the other sex. Let's take a look at how that could be. An example is something that I have no familiarity with whatsoever, which is male pattern baldness. It's called male pattern baldness. That's one of the reasons I picked this. But is it possible for females to have this condition? It definitely is possible. But let's see why so many more males have it. So to avoid confusion about the dominance relationships, I'm going to call the baldness allele, if you will, I'm going to call it B1. And non-baldness is going to be B2. So there's three possible, this is the best way to think of this. There's three possible combinations, right? You could be a heterozygote, you could be a homozygote. But here's the thing. So in men, the B1 allele acts in a dominant fashion, which means all you need is one of them in order to exhibit the trait. So this guy and this guy both would be exhibiting the trait. This guy not, right? What if we did the same thing for women and said there's still three possibilities? Remember, because it's not on the X chromosome or anything. I'm making these subscripts. I apologize. I don't want to do that. Hard enough without making it worse like that. So you could be a heterozygote or a homozygote either way. Now, if you're a woman, the interesting thing is the B1 allele acts in a recessive fashion. So the only woman here that's going to exhibit baldness is that one. Because as long as there's one B2 allele present, it's not going to happen. So again, this does have to do with the hormonal environment. It probably the amount of testosterone present and some other factors. But it's sex influenced. The manifestation of the trait is influenced by the sex of the person who has these alleles. Now, an important thing is, well, first let me just mention, women do have this. You might say, I never saw a woman. Well, for whatever reason, society has deemed that it's okay, if you will, for men to be bald, but it's not as acceptable for women. So you tend not to see it because they'll usually, understandably, get a wig or something or do whatever. But the other thing that's important is this is a simplification. We have to do it this way, but male pattern baldness is not fully understood. You can have the gene and you're going to exhibit some type of pattern, but that's why it's called a pattern. Like some men will just have a bald spot in the back. Some people have a receding hairline from the front. There's all different patterns of ways that you can lose your hair, right? These are influenced probably by other genes, probably by the environment. It gets very, very interesting and complicated. Another myth that I've heard, it is a myth, is that men get the genes for being bald from their mother only. This is not true. So from the mother's side of the family. It could be from your father, from your mother. Men just need that one allele, whereas women would need two. We didn't go into allele frequencies yet, but just think of it this way. This will explain it. Say the frequency of the B1, the baldness allele, is 10% in the population, right? What that basically means is that any male that is born has a 10% chance of getting one of those alleles, and therefore, I just made up the number, will have that sort of a probability of losing their hair. It's actually a little, well, what's interesting as you get older, you probably know this, there's more and more of a chance of exhibiting this trait. So that's another variable to throw in. But my point was going to be, for women to get it or exhibit the trait, they have to get it 2 times. So it's 0.10 times 0.10, which means if we were to accept the idea that 10 out of 100 men were going to get this, only 1 out of 100 women would be homozygous and therefore exhibit the trait. So that's what it means. So it's rather interesting, actually. We don't totally understand baldness. If we did, somebody would be very rich and I would have hair. I'll see you again real soon at another genetics session.